Now, we showed that if k is a pseudoprime to base 2, then 2 to the k minus 1 is another pseudoprime. Could we find pseudoprimes to other bases? Well, let's try to generalize our argument. Suppose p is prime, because we should always start with primes, and a to p minus 1 is a pseudoprime to base a, where a is greater than 2. Then a to power m minus 1 is congruent to 1 mod m, and we also want to have a to power p minus 1 be a factor of a to the m minus 1 minus 1. Note, in order for this to happen, then we have to have this second factor where the terms in that second factor have to have the form coefficient times a to power m minus 1 minus a multiple of p for k equals 1, 2, 3, and so on. And the sequence of terms has to end with a constant, so m minus 1 minus kp must be 0 for some value of k. Consequently, p has to divide m minus 1. So suppose p actually does divide m minus 1. Well, we know that m is a to the p minus 1, so p has to divide a to the p minus 2. Consequently, a to the p is congruent to 2 mod p. But if p is prime, this means a to the power p minus 1 is congruent to 1, so this congruence reduces to. Consequently, if p is prime and a to the power p minus 1 is pseudoprime, a has to be 2, which we've already disposed of that case. So suppose we don't commit ourselves to the form of m and simply require that it satisfy Fermat's relationship. And we'll make our lives easier. We can assume anything we want as long as it's explicit. We'll assume that m is an odd number. Then m minus 1 will be even, and we can assume that m minus 1 is 2 p q for some prime p and some other factor q. We don't really care about that other factor. And so that means a to the power 2pq is congruent to 1. And let's again assume that a to the power 2p is congruent to 1. So that means m is going to divide a to the power 2p minus 1. And the reason that we've made these assumptions is now we have some obvious potential factors. The obvious factors of a to 2p minus 1 are a squared minus 1 and a to p minus 1. But we've already determined that m can't be a to the power p minus 1 for any a greater than 2. And a squared minus 1 is actually kind of boring because we chose the base, so it's either going to be pseudoprime or not for a specific value of a. But let's look the other way. We know that a to p minus 1 must be a factor of a to 2p minus 1. In fact, we can do the factorization, and we can see that a to p plus 1 is another factor. So could m be 1 more than a power of a? Well, let's suppose m is 1 more. We find. And so we want to determine if the right side has a factor of a to the p plus 1. So again, let's think about that. If I can write this as a to the p plus 1 times something, the terms of the other factor must be of the form a to the power a to the p minus a multiple of p for k equal 1, 2, 3, and so on, eventually ending with a constant term. But this would require a to the power p minus kp is 0 for some k, so a to the p must be congruent to 0 mod p. Since p is prime, this requires p divides a. However, if a is odd, then a to the p plus 1 is even, and clearly non-prime, so it's a really bad pseudoprime because it obviously isn't prime. So we do care mostly about the case where a is even, but if a is even, there's only a few primes that could divide it. And this suggests a way we could find a pseudoprime. Choose some even value a, find all primes where p divides a, then a to p plus 1 might be a pseudoprime. We could try this, though since only a few primes will divide A, this promises at best a limited yield. There's one last obvious factor. We know that a squared minus 1 divides a to the power 2p minus 1. The other factor is not easily expressed, but we could still define m as that quotient. Now if m is the quotient, then if we multiply across we get, but the left side is a multiple of p, so if I work mod m, I get, so a to the power 2p is congruent to 1. But remember we assumed m minus 1 was 2p cubed, so if I raise both sides to the qth power, I get, and a to the power m minus 1 is congruent to 1 mod m, and so m satisfies that pseudoprime relationship to base a. And this gives us another way to construct pseudoprimes. So this time let p be an odd prime, and we'll compute m equal 4 to even values of a. If p divides m minus 1, then m is a pseudoprime. So if p equals 3, we find that a equals 6 gives us, and 6 does in fact divide 217 minus 1, so 217 is a pseudoprime to base 6. And we'll go ahead and verify 6 to the power 216 is in fact 1 mod 217. And we'll also note that 217 factors, so it's not actually prime. We could also choose a and try different primes, but our numbers get very big very quickly. For example, if a equals 22, we go through our list of primes and we find p equals 11 produces the pseudoprime to base 22.